Hello everyone, this is Dr. Young, and in this video we're going to talk about acyl halides, which are probably the most useful carboxylic acid derivative synthetically of all of them that we're going to talk about. So remember we had this reactivity sort of grid, this ladder here, and I mentioned that we can take our carboxylic acids and we can turn them into these acyl halides. And what was super important about these acyl halides is that they are the most reactive, we talked about this before, they're the most reactive. And you can turn them into anhydrides, esters, amides very, very easily. You just add the group that you want to be attached to the carbonyl. And so that's what we're going to kind of take a look at, is a few examples and what those mechanisms look like. So the formation from carboxylic acids, just like we had on that previous slide, we usually just, we start from the carboxylic acid, whatever it is we want. So let's just say we have this carboxylic acid here. And if I want to turn this into an acyl chloride, I'm just going to do the same, use the same reagent that we used before when we wanted to turn other OHs into chlorines, which is SOCl2. So you'll see SOCl2, or in other words, thionyl chloride. And then you may or may not see some sort of base here, where this base can be something like pyridine, which is abbreviated PY, or triethylamine, which would be abbreviated, TEA. So usually there's some sort of base there. You may not see a base written. That's okay. You know that you're going to turn that OH into a Cl, right? That's the big key thing. OH is now Cl. Now another reagent that you have already seen before also is the PBr3, right? So if I had a different carboxylic acid and I wanted to turn that into an acyl halide, I could turn it into the acyl bromide instead. That's totally fine, right? So I could add PBr3. And this also will have some sort of base because you generate an acid, so also have some sort of base here. Let's just put triethylamine for this one. And so you can easily turn your carboxylic acid into an acyl bromide. Now, it doesn't matter. I could have used PBr3 on the top one. I could have used SOCl2 on the bottom one. It doesn't really matter. There's no reason to use one versus another. And nor is there really a great reason to use bromine versus chlorine. Yes, bromine's a little bit more of a better leaving group, but SOCl2 is super small and common and cheap. And so we see a lot of acyl chlorides. But either one is fine. Either one is super reactive. The last reagent that you may see here, and I'll just do a third example of a carboxylic acid, is you might also see oxalyl chloride, which you may remember from the Swern oxidation. Oxalyl chloride does the same thing. So any of these three reagents will turn your carboxylic acid directly into your acyl halide, whether it's chloride or bromide, right? So with PBr3, we turned it into a bromide. With the oxalyl chloride, right, it's got Cl's on it, we turn it into the acyl chloride. And again, the point of this is that we take that carboxylic acid, which we said was not electrophilic, right? All it's going to do with a nucleophile is probably just going to do an acid-base reaction to an acyl halide, acyl chloride or bromide, which is very electrophilic, very reactive, very reactive electrophile. Right, so this gets us to our top of our ladder. We can turn those into anything we want. So let's look at a summary of that. Right, so we had just that general addition elimination reaction. And so I could take, for example, this carboxylate salt. Right, which probably was some deprotonated carboxylic acid. And if you had a carboxylate salt to an acyl halide, you're going to make an anhydride. Right, because the idea is that this OR piece is now this the O-cetyl-1-OR piece is now that piece. You've just replaced the chlorine with that new chunk, right? So we're just replacing whatever that leaving group is with whatever the new thing we want is. So it's easy to go from an acyl halide to an anhydride. And again, remember that's moving down that ladder of reactivity. Same thing if I want to just add an alcohol. If I want to just add an alcohol, that means I'm just going to add this piece, right? This OR piece is this OR piece, and I can make an ester. Easy breezy. I just have the acyl halide, add whatever alcohol I want, and then I get the ester. Great yields. And then lastly, I could add an amine, right? So this could be ammonia, right, which is NH3, or this could be a primary amine or secondary amine. And any one, right? This, in my case, I drew a secondary amine, a generic secondary amine, but it could be primary or ammonia. It just can't be tertiary because you have to lose an H at the end, right? You'll notice that the H that's on the secondary amine is no longer there. And you do need to add excess of this stuff, right? At least 2 equivalents, because what's going to happen is that some of your amine is going to end up picking up the acid that is formed when you react away your acyl halide and your H disappears from your, not disappears, but your H falls off of your nitrogen. And I'll show you an example of how these reactions are acidic. They always produce acids and they always drop the pH. So this would be like your first equivalent. Your first equivalent would add, and then your second equivalent is there to soak up the H+. And if you don't add excess of that amine, then your reaction is only going to go 50% because your amine is going to get protonated, and once it's that ammonium salt, it's no longer nucleophilic, so it's no longer going to add. So let's look at some of these mechanisms. So let's say we have the example, I'll do 3 real quick here for you. So let's just say we have an example where we do have an acyl, let's say bromide, and I am going to add a carboxylate salt. And let's say it's the sodium salt, and I'll add my lone pair since this is a mechanism, so I need to show all of the arrows. The idea here, right, if I put my partial charges on here, so partial positive on my, partial negative, excuse me. Partial negative on the oxygen and the bromine, partial positive on that carbon there. I have a full-on negative on my carboxylate. So I'm just going to have that carbon come in and attack that carbonyl carbon of the acyl bromide. The weakest bond on here is the pi bond, so those kick up. Right, so here's your addition step. So now I have an O minus. I have a bromine. And now I have an O, double bond O, CH3. And I'm going to draw the CH3 out just so we can kind of keep track of that piece. And then we ask ourselves the same question that we always do, is that, well, when this, is the lone pair stuck on the O? And in this case, no, because we do have something that can leave. Right, I'm not going to break the CC bond on the left because those are real strong. I could break the CO bond on the right, but I just added that, so that would just be going backwards, so that's why this step is reversible. Or I could have the bromine leave, which is the best leaving group, and so is going to be the major product that's formed here. And we're going to end up with double bond O, so I have a double bond O now, but I still have the O CH3, this acetate piece. And then I have Br minus hanging out next to my Na plus, right? So I've made an anhydride in this case. I made an anhydride, right? I went from the acyl bromide down to the anhydride. Now, while this reaction works, this is totally fine and everything, we don't often make anhydrides in organic chemistry. We usually just buy the ones we need. Usually they're just like acylating agents. And I'll talk more about that hopefully here in a second. But I should put that. I don't think I have a slide for that. Let me add that here in a second. We usually just use them as acylating agents for things like Friedel-Crafts reactions, and let me show you that. And anyway, so this would make an anhydride, but usually we just buy them as is because we don't need them to be asymmetric like this one is. Now let me show you one more mechanism with a neutral nucleophile, right? This nucleophile over here at the top, this was negative already, so it was an anion, right? So here my nucleophile was an anion. Nuke is an anion. Let me show you one where the nucleophile is neutral, because it's slightly different. It's very, very similar, but slightly different. And so let's do an acyl chloride this time, not that it matters. I'll just add some other junk on here. And let's say we'll make an ester this time. So I'm going to add OCH3. right? So again, in this case, now my nucleophile, my nuke is neutral. Still gonna be a very similar reaction. I just need to deal with that H is the point. So partial negative, partial negative, partial positive, negative, positive, positive. Same thing, my nucleophile is gonna attack that very, very reactive carbonyl. Those electrons kick up. So now we have this O minus, a Cl, and an OCH3. And the same sort of question is are the electrons stuck up on that negative O? No, this can drop down and kick something out. Yes, it could kick out that OCH3, which is going right back, or it could kick out the chloride, which is going to move forward here. So now I have double bond O, OCH3, but this still has that positive on it. And it may have lost it before this step. Where it loses it, whether before this or right now, is totally fine. But either way, it's going to lose that H, right? And so it's going to lose that H to give us our product, to give us our ester. So now it's just OCH3. And then we have an H plus, and we have, in this case, Cl minus. So this is what I mean by when I say, when you add like a neutral nucleophile, you tend to get more acidic. The reaction's getting more acidic. Reaction gets more acidic. And so sometimes either people will add bases to this so that it doesn't get too acidic, again, like triethylamine or pyridine or something. Or if your whatever molecule you're working on can handle the acid, then you don't need to worry about it. You can just neutralize it at the end. But let me add a slide to talk about why we might care about these, right? So one is to like move through all of these carboxylic acid derivatives, but you've actually already seen these, right? You've seen acyl halides in the Friedel-Crafts acylations. Right? Remember where you had like an aromatic ring, and maybe you had, let's say we had a bromine on here already. We said that, I can just acylate it. I can add an acyl halide, and I use a catalyst like aluminum trichloride, and that will acylate my molecule. And so we totally can do that still, right? That's something that acyl chlorides can do. It's not really the additional elimination reaction that we typically expect them to, but I just want you to remember that we can do this with the aromatic compounds. But how you're going to see this maybe slightly tweaked is that maybe it's slightly tweaked because I have, let's say I have some molecule like this. And I want to turn it into this. Let's do something like that. Now what I'm seeing here is that I have a new CC bond. And it looks like it came from a Friedel-Crafts acylation. But I don't have yet a carboxylic acid derivative. I don't have that acyl chloride yet. So what I can do is I'm going to have to do this sort of chemistry and then do a Friedel-Crafts reaction afterwards, right? So for example, I could do a hydroboration. So step 1, BH3 to get an OH out there. Add hydrogen peroxide, sodium hydroxide, and water. All right, so that's going to give me this. Now I know how to oxidize that up. I can use Jones or oxone, something with water so it fully oxidizes. So let's just put the Jones stuff, chromium trioxide, H2SO4, and water. That's going to give me a carboxylic acid, which is great. But what we've just learned is that I can add SOCl2 and let's say pyridine to turn that into the acyl chloride, which I can then do my Friedel-Crafts reaction with, right? Then I can add, for example, the toluene that it looks like we're adding it to, and the catalyst, AlCl3. So I can kind of mix this up and make it look backwards. Normally we started with the aromatic ring and then we added reagents to it. We can also think about it the other way around, which is that we're going to make that reagent that I'm going to then use to acylate some new aromatic compound. So keep that in mind. We have seen acyl halides used before in Friedel-Crafts acylations. Now here's some other more traditional examples. So again, if you're looking at this, right, I see that I have an acyl halide. I see that I have an alcohol. So I know I'm going to make an ester. So all I need to do is I just need to take whatever that acyl halide is, and I just need to add the ester piece. So it's a propyl piece. So 1, 2, 3 carbons. That must be my ester. So this would be some sort of propyl, what is this, butanoate, something like that, propyl butanoate, to make an ester. Again, really easy, really fast reaction. Here's another example, only we're going to go work backwards here, where it looks like, again, I'm making an ester, and it looks like the ester has an isopropyl on it, so I just need to add isopropanol. I just need to add isopropanol to this acyl halide because that will react. It will go, it'll attack the carbonyl, electrons kick up, kick down, kick out the chloride, and then I've got an ester. So that's no problem. For the amide here, looks like we formed an amide. Again, I just need to add whatever this is as an amine. So it looks like I have this 5-membered ring with a nitrogen in it. And I know that I'm going to need excess, right? At least 2 equivalents. So I'm just going to write excess. I'm going to draw that 5-membered ring. That's all. Oh, wait a minute. Will that react with a carboxylic acid? No, it will not. So I need to make that carboxylic acid more reactive by first adding, let's say, PBr3 and TEA to turn it into the acyl bromide. And then step 2, let's add my 5-membered ring amine, and we'll add excess of it, right? So now I have to do step 1, step 2, right? Just adding the amine to that carboxylic acid's no good. It's going to be a really, really difficult reaction that would require crazy high temperatures and stuff. No one does that. Much easier reaction would be to turn the carboxylic acid into an acyl halide, add the amine, you're done. And then lastly, we have an example of more of a synthesis. Okay, we're going to need a lot of steps here to do this one. And it looks to me like this carbon 1, 2, 3 is probably this carbon 1, 2, 3. And what I'm noticing here is that I have an ester. Right, I have an ester, which I know I'm going to make from a carboxylic acid. And I know lots of ways to make carboxylic acids, right? I can oxidize up alcohols. I can do SN2s with acyl halides to make a nitrile and then do a hydrolysis on them. I could turn an alkyl halide into a Grignard reagent and bubble through CO2 and protonate it to make a carboxylic acid. So I got a lot of ways, but I do see that this is a new carbon here, right? I have 1, 2, 3 carbons on the left, but a 4th one here. So I do need one of the ways that creates a new carbon. So there's a new carbon here, which means I need to either do the nitrile way or the Grignard way. So I'll just pick whichever one I want here. So first step, let's do the Grignard way. In fact, I need to do the Grignard way because if I do the amide way, I'm going to hydrolyze. When I do the hydrolysis of the nitrile, I'm going to accidentally destroy that acetal. So I cannot do the nitrile way. I have to go the Grignard way. So I will first add a little magnesium to make this molecule my Grignard reagent. I'm going to bubble through a little CO2 next. So I have my O minus. You can use the thionyl chloride or SOCl2 or whatever on the carboxylate. You don't have to have the carboxylic acid. You can protonate this if you want, but you don't have to. You can skip that. Let's add SOCl2 with triethylamine so that I don't get too acidic and hydrolyze away my acetal. So now it's chlorine. We're going to go ahead and add that alcohol. Looks like the alcohol that I need to add is HO. Just that one. So I'm just going to add that alcohol. That'll give me the ester. Let me give myself a little more space. So now I've got almost the last thing, and then I'll use H3O plus to get rid of the acetal to give me back my my aldehyde there. Now note with this one, I'm adding H3O plus, but I'm not going to warm it. Acetals fly off as soon as you expose them to acid and water. To hydrolyze an ester, I would really need to heat it up. Esters are pretty resilient to hydrolysis. You gotta warm them up to get the reactions to go. So this would be no problem. I wouldn't have to worry about hydrolyzing the ester. Anyways, I hope you see how useful acyl halides are. They're a really easy way to make any of the other carboxylic acid derivatives directly, except for the nitriles, but very, very, very helpful. So definitely use them. Do lots of practice. Good luck.